Cars have reshaped our urban landscape, and autonomous vehicles will be the next revolution. While the possibilities of autonomous vehicles are exciting, there are some immediate challenges automakers must overcome to realize this future vision of mobility. There are hundreds of different sensors that need to work together, and software algorithms that need to synthesize the information to ensure the vehicle responds with the best behavior. Think of autonomous driving technology as learning to drive, and each component in the system needs to be fully tested, including corner cases, many of which are currently impossible to test in a lab environment. The radar sensor is a major component of a vehicle's ability to detect its immediate environment. Primarily installed as a front-facing module that detects objects ahead of the host vehicle, it's a staple of autonomous driving features, enabling the detection of objects in various blind spots and enhancing its vision. One of the necessary, though insufficient, conditions for testing a radar-based autonomous feature using emulation is to generate a realistic and complex scenario for the radar sensor to deal with. At Keysight, we invented something that can help. The Radar Scene Emulator, or RSE for short, acts like mmWave VR goggles for radar sensors. An array of mini radar pixels forms a screen. Each pixel represents a point on an object, including distance, velocity, and size. Together, they generate a realistic outline of a 3D radar object. Items are represented by multiple pixels according to their width, depth, and height. Multiple objects close to each other at a farther distance will become separate as they get closer. Pixels work together to create a scene with many static and dynamic objects across a broad field of view. Using this technology, we can emulate complete scenes to the physical radar module, testing the radar front end and detection and categorization algorithms. Let's look at a few vital scenarios that are dangerous to test on the roadway and why those are hard to test in the lab without an RSE. Here, the host vehicle turns right on a street with traffic on both sides. Pedestrians and cyclists cross the street in the same direction of travel. The radar sensor must simultaneously detect vehicles and pedestrians as they cross the street. To accurately identify and follow the motion of an object, the radar sensor clusters reflections together. This is known as extended object tracking. Simulation software is used to model the radar sensor, and labeled data is used to see how it behaves. As the radar front end may act differently than expected, it could completely miss seeing the difference between the person and the car. This approach is great for the first pass, but is incomplete. Using only the digital processing portion of the physical radar, labeled data is injected directly, bypassing the radar's point cloud detection and clustering capabilities. A radar target or echo generator is used to simulate individual targets. This approach limits the details of the objects with only one point per object. All of these methods, whether used in isolation or together, are incomplete without being integrated into a prototype vehicle. Now let's look at how this is done in a lab environment with Keysight's RSE. For the autonomous driving feature to pass the test, the vehicle will need to detect different objects on the road. The simulation software shows the scenario, while the RSE software window shows a bird's-eye view of the radar vision. The scenario contains many green points. These are the ones that the RSE generates based on the scenario. Notice when the pedestrian is close to the host vehicle, there are 2 green points. The red points are outputs from the radar device and represent the detections. Overlapping green and red points indicate a correct detection in the expected location. Notice how you can visually identify other traffic participants. The RSE Extended Object Generation feature allows testing the radar algorithm's detection capability based on multiple reflections and helps to validate the 3D outline of objects. Building on the previous scenario, a rushed pedestrian dashes across the street close to the host vehicle. The radar should detect this pedestrian just in time to bring the car to a halt and wait to proceed until the pedestrian has run across the street safely. Although this scenario is typical in an urban setting, It's difficult to test it realistically in the lab. Considering the same three methods as before, simulation software does not test the reaction of the real radar. Injecting objects via CAN into the ECU does not offer any insights into potential delays for this time-critical scenario. And radar target simulators are not able to generate a target this close to the host vehicle. All three methods offer insight into how the radar will behave, but are incomplete. Returning to the RSE, in order to test how the algorithm can handle an unexpected action within 2 meters of the AV, the host vehicle is expected to hit the emergency brake to avoid hitting the pedestrian. The detection, perception, and decision-making processes must work flawlessly and extremely fast in such conditions. A few dropped frames from a radar sensor can be the difference between life and death in a situation where the object on the road is just a few meters away. This is valuable, as it can help to test the center and the edges of the radar's field of view at short distances and in time-critical conditions. In our scenario, even more traffic has been added. The radar must perceive that a new object has entered the scene on the edges of its field of view, while tracking all the other objects. Again, easier said than done. Replicating such a scenario in the lab with current equipment is practically impossible. Software simulation works without the physical radar and leaves more risk to prototype testing, as potential reflections off the bumper at the edges of the radar field of view may create ghosts. Injecting objects as before will not include the antenna effects into the test. While a radar target generator can only show a handful of targets simultaneously, ignoring the periphery of the radar means the wide field of view capability available with short-range radar sensors is untested or oversimplified with just 2 or 4 targets. What if you could find and correct those errors earlier in the design cycle? With the RSE, this type of test setup is possible. To fully understand and adjust for the scene, you need to be able to see all the objects all the time. The RSE addresses this by employing a very wide 140-degree field of view that holds 64 rixels in one row. The rixels are individually controlled and can all be simultaneously switched on without interference between them, enabling you to depict a large number of objects from a broad field of view. If we combine the above into one scenario, we get a complex urban scene with pedestrians and cross-traffic. In the automotive industry, we are replacing drive tests on the track or the public roads with real-time simulations and hill emulations, thus reducing costs and emissions, slashing time to market, and allowing a glimpse into otherwise impossible or corner case scenarios. Consequences of incomplete testing can mean poor consumer report ratings, potential recalls, and in the worst case, pedestrian deaths caused by an autonomous driving feature. The RSE will not completely eliminate roadway testing, but it can save valuable time and money by allowing you to emulate in a lab environment. We challenge you to bring us a scenario that the RSE cannot test.